There is from Department of Mathematics, University. So I think that's how come to present here.
Okay. Okay. So, very good morning to everyone. This is Saurabh Mandal from Department of Mathematics, University of North Bengal. The title of my today's presentation is The Degree of Roughness. Actually, this phrase comes from the definition of rough convergence. And since 2001, every extension on rough convergence has been done by considering the degree of roughness as a non-negative real number. For the first time, we have extended this rough convergence in a topological space by considering the degree of roughness as a neighborhood. Here is the outline of my presentation. Before going to rough convergence, I say few words about bisection method, and it is used to find some approximate root of some equation up to some desired level of accuracy, and it is based on some theorem which says that if f be a continuous function in a closed interval ab and the product of f a f b less than 0, then there exists at least one real root alpha of the equation in between a and b. So what is the procedure? We first consider the interval as the interval f0 and b0, and we say the x1 as their midpoint. Then we calculate the value of f at that point. If f of x1 is 0, then x1 is a root. Otherwise, one of these following conditions is true. Suppose f of a0 and f of x1 less than 0. Then from this previous theorem, alpha lies between a0 and x1. So we consider the closed interval a1 b1 as the closed interval a0 x1, and then we set x2 as their midpoint, and doing the same procedure. And in this procedure, we can get x2, and in a similar manner, we can get a sequence which converges to the actual root alpha. Now, suppose we need to find the root up to correct up to 3 decimal places. Then there is some positive measure integer k, so that xk minus xk plus 1 less than r. And this surely implies for all I greater equal to k, the non-modulus difference between xk and xk less than r. So this implies the root of fx equal to 0 are xk, xk plus 1 and xk plus 2 and so on. So there are infinitely many roots. So in bisection, hello, hello, hello.
Please continue, sir.
Okay. So in the bisection method, we find a generating sequence such that after finite term, the difference between sequential term and the main root become less than r. Now, just remind the definition of classical convergence. In that case, we have arbitrary positive real number instead of r. So from bisection method, we can go to the definition of classical convergence. And with this idea, in the year 2001, a Vietnam mathematician H.X. Fu first introduced the notion of rough convergence in a non-linear space. Come to the definition. Let R be a non-negative real number, then a sequence is said to be rough converging to some extra with degree of roughness R if for any positive epsilon, condition 1 is true. Now just put R equal to 0 in the condition 1, we are getting classical convergence. Here is the example which shows the difference between classical convergence and rough convergence. In this example, we have considered two sequences, xi and yi. For the first sequence, it is classically converging to the unique limit point 0. But in the case of rough convergence, it is rough converging with degree of roughness 1 in the closed every point in the closed interval -1 to 1. And for the second sequence, we have considered a finite oscillatory sequence. So it is surely not classical convergence sequence, but the rough limit set is look like this. Now, from this example, two things is clear. The first one is the rough limit point is not unique, and the second thing is the rough limit set in R is closed, and it is not closed. It is also convex and bounded. Now, there is a question: is it possible for any sequence to be rough convergent? If we just consider the sequence xi equal to I square, or we can consider any unbounded sequence, then there does not exist any positive part for which the R limit set become a non-empty set. And there is a theorem which says that a sequence is bounded if and only it is rough convergence. Now move to high convergence. It is the generalization of statistical convergence, and it is based on the structure of ideal of natural number. Now, what is an ideal? An ideal is a collection of subsets of natural numbers such that it is closed under finite union and subset. It is called non-trivial if it does not contain the whole set, and a non-trivial ideal is called admissible if it goes under all singletons. Now, here is some example of ideals. In the first example, we have considered all the finite subsets, and the second, we have considered all the density zero subsets of natural number. And in the third one, we have considered all decomposition of natural number, and I lambda is the collection of all such D such that D intersect only finitely many values. Luckily, all of them form an admissible ideal. Now come to the definition of I convergence. Let I be a non-trivial ideal, then a sequence is said to be I converging to X if for any positive epsilon, the set A epsilon is in I. Now, like classical convergence, in I convergence, the limit point is unique. So, the question, does classical convergence imply I convergence? Let X is a classical convergence sequence which converges to X. Then for any positive epsilon, the set A epsilon is a become a finite set. So for if we consider any admissible ideal, then A epsilon is in I. So we can say that if I is an admissible ideal, then classical convergence implies I convergence. And what is the converse? Is there exist any ideal, or is I convergence implies finite classical convergence? If we consider the ideal IF, that is collection of all finite subsets, then ideal convergence implies classical convergence, because in that case A epsilon can only be a finite set. Now we'll give an example. In this example, we consider the sequence in this following form. That is xi equal to I for all odd I, and it is 1 otherwise. Then if we consider the ideal I lambda, then it is ideally converging to the point 1. But this sequence is an unbounded sequence. So a I converging sequence may be an unbounded sequence also. Now come to the definition of I boundedness and I non-free subsequence itself. And it can be easily proved that a I convergent sequence is always I bounded. Now the definition of I cluster point. An element J is said to be I cluster point of subsequence xi if for any positive epsilon condition is true. Now from the previous example, we see that a I convergent sequence may be unbounded. So I convergence does not imply rough convergence, because in rough convergence a sequence should be bounded. So is it possible to combine these two convergences? Yes, it is possible. In 2013, Paul et al. Introduced the notion of rough I convergence in a nonlinear space. Here is the definition. Let R be a non-negative real number, then a sequence is said to be rough I converging to some extra if condition 4 is true. Now, if we consider R equal to 0 in the condition 4, then we are getting I convergence, and if we consider the ideal IF, then we are getting rough convergence. And like rough limit set, rough ideal limit set is also closed, bounded, and bounded. So, what is the difference? Here is the difference. In this example, we have considered the sequence in the following form. Then the sequence is neither rough convergent nor ideal convergent for any ideal. But if we choose the degree of roughness are equal to 1, and if we choose the ideal term, then rough ideal limit set is the closed interval 1 to 2. Now, very recently, Ghosal et al. Extend this rough I convergence a little bit more and introduce the notion of rough weighted I convergence in a metric space. Come to the definition. Let R be a non-negative real number and Ti be a weighted sequence. Then a sequence is said to be rough weighted I converging to some extra with degree of roughness R if for any positive epsilon condition 5 is true. So what is the extra term in condition 5 from rough I convergence? Here only we here the extra term is Ti. So if we consider the weighted sequence as a constant sequence 1, then we are getting rough I convergence. And in this definition, each term of the weighted sequence is greater than some positive real number delta. That is because if we consider the weighted sequence from negative side of real number, then this quantity become a negative quantity, and this collection become an empty collection. So what happens? In that case, any sequence can converge to any limit point. So we omit that part. And same thing happens if the weighted sequence converges to 0. We'll give an example. In this example, we have considered the ideal I delta and we have considered the sequence in this form. Then for any positive real number R, the rough ideal limit set is the closed interval minus R to R. But if we consider the rough weighted ideal limit set, then if R less than 1, then it becomes an empty set. And if we consider R greater equal to 1, however large, then it becomes a singleton set. And the next theorem says that the limit set containing at most one element if the weighted sequence is not I bounded, and it is always and bounded. Now, come to the definition of rough convergence one set. Here is the definition. If x rough converges to x star, it implies this condition. If we simplify this in Euclidean norm space, then this happens. And where minus R to R is a fixed neighborhood of 0 in real number system, and this is an arbitrary neighborhood of 0. So can we replace this neighborhood by a fixed neighborhood and this neighborhood by an arbitrary neighborhood in a topological space? If we do so, then we have to add two neighborhoods, and that is not possible in a topological space. So we have considered locally solid space, and there is some preliminaries of locally solid space, and in that space, the basis element satisfies this condition. That is, each basis element is a balanced set, each basis element is an absorbing set, and for each basis element there is another basis element, so that W plus W contains. Now, a set in a locally solid space is said to be topologically bounded if for any term u of theta there exists some positive lambda such that A is contained in lambda mu. Otherwise, it is called lambda tau unbounded sequence. Now come to the main definition. Rough weighted I tau convergence. Here we consider I as an admissible ideal and Ti be a weighted sequence. Then a sequence in a locally solid space is said to be rough weighted I tau convergence to x star with respect to roughness V, where V is a fixed tau neighborhood of theta. If for every tau neighborhood U of theta, condition 6 is true. Now, in the case of metric space, we put two restrictions on the weighted sequence, that it can't be negative and it can't converge to the 0. But in this case, we can omit one condition, that is, it can be from the negative side, but mod of each term greater than some positive real number delta, because here the basis element satisfies the balance set. Balance is the balance set, so this condition true. Now we will give an example. In this example, we have considered the locally solid space R square, where the norm is defined by norm of xy equal to mod x plus mod y. In this example, we have considered the sequence in this form. Then, if we picturize this example, then in the left hand side, this is contained the degree of roughness set V, and in the right hand side, there is the limiting set, and it is an union of sin x and s square. So from this picture, it is clear that this set become a non-convex set. So if we start from rough limit set, rough ideal limit set, all of them are convex set. So is there exist any extra condition which could transform this limiting set to a convex set? Yes, there is. If the degree of roughness set is convex, then the limiting set is also convex. But the condition is only a sufficient condition, because if we just replace the norm by max norm in the previous example, and if we consider this degree of roughness, then we are getting the limiting set as a statement, which is surely a convex set. Now, in metric space or in norm space, we can calculate the diameter of subset. So we can easily say that whether a set bounded or not. But in that case, that is not possible. So we have considered this theorem. Let L tau be a housed of locally solid space, and we consider the degree of roughness from the basis element, so that V plus U is also basis element. Then if we consider the extra from the limiting set, then the limit set contained in that set. And from this condition, it is clear that if the degree of roughness set is a tau bounded set, then the limiting set is also tau bounded. Now, two questions arise. What is the guarantee of getting such P? To answer this, we have considered the locally solid space R square with Euclidean norm, where the basis element are given by US. And if we consider the V as U1, or we can consider U alpha, where alpha is a positive real number, then it is clear that V plus U is also a basis element. Now, there is another question: what is the guarantee of getting such X star for any sequence? For this, we have introduced the notion of weighted I tau boundedness, and we have proved that if the sequence is weighted I tau bounded, then for every tau neighborhood V of theta, there exists some positive mu, so that the limiting set with degree of roughness mu B become a non-empty set. But this is also a sufficient condition, because in this example, we have considered the locally solid space R square with Euclidean norm, and we have considered this sequence. Then the point point AB is in the in the limiting set for any degree of roughness. But from this construction, it is clear that this is not a weighted item bounded sequence. Now, in metric space, we have seen that the limit set contain at most one limit point if the weighted sequence is not I bounded. But here, that may not be true, because in this example, we have considered the weighted sequence as a I unbounded sequence, and we have considered this sequence. Then we have considered the degree of roughness as the tube. Then we are getting the limiting set as x-axis. So this is surely an infinite set. And our next theorem says that if the weighted sequence is not I bounded and the degree of roughness is a tau bounded set, then the weighted item limit set can contain at most one limit point in a housed up locally solid disk space. So here the cardinality of the limiting set not only depend on the weighted sequence, it also depend on the degree of roughness set. Now we'll discuss about closeness property of the limiting set. And it is closed if the following condition, one of the following condition is true. If the weighted sequence is I bounded and the space has first countable property, otherwise if the weighted sequence is not I bounded and give it tau bounded set in a housed up space. Now if we commit the condition that V is tau bounded, then what happens? If in this example we have considered V as a tau unbounded set, then we are getting the limiting set this, which is neither closed and not open. Now we move to the definition of weighted I-tau bounded cluster point. An element is said to be weighted I-tau cluster point of some sequence xi if for every tau neighborhood U of theta condition 9 is true. Now next theorem is concerning about the existence of the cluster point, and it is as follows. Let L tau be a locally solid disk space and the weighted sequence is I bounded. Then if a sequence has a I non-thin subsequence which lies on a compact set L, then the weighted I-tau cluster point set become a non-empty set. If we omit just one condition from here, then the theorem may be false. Because in this example, we have considered three cases. In the first case, we have considered the sequence and the weighted sequence in the following manner. Then the sequence does not have any I non-thin subsequence which lies in a compact set, and the weighted sequence is a I unbounded sequence. So the cluster point set become an empty set. And in the case we just replace the weighted sequence by a I bounded sequence. Then also the weighted I-tau cluster point set become an empty set. And in the case 3, we have considered the sequence which has a I non-thin subsequence which lies in a compact set of L, and Ti is a I unbounded sequence. Then also the weighted I-tau cluster point set become an empty set. Now we'll discuss the closeness property of I cluster point. Professor Das have already shown that in topological space, I cluster point set is closed. But in the following example, we have considered a decomposition of natural number, and with that help of this decomposition, we have constructed the sequence. Then for every natural number j, 1 by j comma 0 is in the cluster point set, but theta is not here. So the cluster point set becomes a non-closed set, and it is closed if the weighted sequence is I bounded sequence. Then the last theorem is about the relationship between the rough weighted limit point set and the weighted I-tau cluster point set. It is given by following 4 conditions, and also if the degree of roughness is tau bounded and the limiting set is non-empty set, then the cluster point set become a tau bounded set. In the case of limiting set, we only need that this condition, P is tau bounded, then the limiting set is tau bounded. But in the cluster point set, we need extra one condition. That is because in the previous example, if we consider if we replace this xk by this sequence, then for every natural number j or j comma 0 is in the cluster point set, so it is an tau unbounded sequence, but the limiting set become an empty set. Next, these two maps are statistically continuous. It is proved by Albert, and in our next example, we will see that that may not be true in our space. In a locally solid disk space, we define this sequence in this following form. Then the weighted I-tau cluster point set contains only 2 points, and and this AB and minus B is not there. So here that may not be true. And from this example, we also say that the weighted I-tau cluster point set is a non-convex set also. And the talk is based on the paper, the degree of roughness. It is a joint work with my supervisor, Dr. Sanjay Kumar.
Thank you, Saurabh. A question. if this are hard, so online participants have please and ask. Any question? So if there is no question, let us ask the second question.
Thank you.
Now we